Hello students, welcome to chemistry class. It is the sixth session of solid state chapter. In previous video we have discussed about the calculations involving unit cell dimensions. In this video I am going to discuss about the close packed structure. Then first we have to understand in solids what do you mean by close packing arrangement. Close packing arrangement means the arrangement at which maximum number of particles occupies minimum space is called close packing. Once again I will repeat, the arrangement at which maximum number of particles occupies minimum space is called close packing, or else the arrangement of constituent particles as closely as possible, it is called as close packing arrangement. And one thing it is very important here. Here let us consider the constituent particles as identical hard spheres and build up the three-dimensional structure in 3 steps. Once again I will repeat here. Here I am going to consider constituent particles. Constituent particles means it may be ion, molecule or atom. Instead of using ion, atom or molecule, here I am going to use the word sphere. Here constituent particles is considered as identical hard spheres and build up the three-dimensional structure in 3 steps. First one is close packing in 1 dimension, close packing in 2 dimension and close packing in 3 dimension. Let us study one by one. First one, close packing in 1 dimension. See here, in close packing in 1 dimension, there is only one way of arranging spheres. There is only one way of arranging the spheres in 1 dimension. 1 dimension means there is only one way. You can there is no another way. There is only one way of arranging the spheres in 1 dimensional close packed structure. That is to arrange them in a row and touching each other. Touching each other. You can arrange in a one row and touching each other, and it is a close packing in 1 dimension. And here coordination number is 2. Here coordination number is 2. Coordination number means what? Then coordination number means the number of nearest neighbors of a particle is called as coordination number. Once again I will repeat, the number of nearest neighbors of a particle is called coordination number. For example, for this sphere the number of nearest spheres are this and this. These two are nearest neighbors particle of this particle. Hence the coordination number in 1 dimension is 2, because here this sphere is contact with 2 of its neighbors, hence coordination number is 2. You can take example this sphere. This sphere is also contact with 2 spheres, another 2 spheres, hence coordination number is 2. Okay, the coordination number in 1 dimensional close packed structure is 2. Okay, next one is close packing in 2 dimension. Close packing in 2 dimension. Already you know that close packing in 1 dimension, there is only one way of arranging the spheres, that is to arrange them in a row and touching each other. Just here also we can build up the close packing in 2 dimensional from close packing in 1 dimension. Just take the row of spheres, see here, and second row place over the first row. Second row place adjacent to the first row or place over the first row. These spheres of the first row and spheres of the second row are exactly aligned horizontally as well as vertically. Okay, means if we call this row as a type, and similarly This row is also called as A type because the spheres of first row and second row are exactly aligned horizontally as well as vertically. Hence, if we call it as a type, this is also A type. And third row is also exactly aligned with the second and first, and fourth layer is also exactly aligned with the third, second and first. Hence, these all row are called as A. Hence, this arrangement is called as A type arrangement. This arrangement is called as A type arrangement. And here coordination number is 4 because here each sphere is contact with the 4 of its neighbors. Each sphere is contact with the 4 of its neighbors. Thus, the coordination number is 4. Coordination number is 4. If we join the centers of these 4 spheres, you will get a square. You will get a square. Hence, this packing is called as square close packing. Hence, this packing is called as square close packing. Square close packing. Similarly, in square close packing, this is one way of arranging the spheres in a two dimension, and another way is there. We can arrange the spheres in two-dimensional in another way, that is called as hexagonal close packing arrangement. This is a square close packing. You can arrange the spheres in two-dimensional, that way is called as hexagonal close packing. So how we can arrange the spheres in hexagonal close packing? Similarly, here also take one-dimensional close packed structure. That is first row. It is called as one-dimensional close packed structure. You can take that row and same row. Place second row over the first row, such that the spheres of the second row fit in the depressions of the first row. Once again, I'll repeat. Place the second row over the first row. The spheres of the second row are fit in the depressions of the first row. See here. This is a depression of the first row, and spheres of the second row is fit in the depressions of the first row. Similarly, here also this sphere is fit in the grooves of the first row. This sphere is also fit in the grooves of the first row. Okay, and if we call it as a type, it is a different arrangement. Hence, it is called as B type. And third row is exactly aligned with the first row, hence it is called as A type. And fourth row is exactly aligned with the second row, hence it is called as B type. And this type of arrangement is called as AB type arrangement. This type of arrangement is called as AB type arrangement. And here coordination number is 6 because each sphere in this arrangement, each sphere is contact with the 6 of its neighbors. Hence, this arrangement is called as in this arrangement, coordination number is 6. If we join the centers of these 6 spheres, you will get a hexagon. Hence, this arrangement is called as, this packing is called as hexagonal close packing. This packing is called as hexagonal close packing. Okay, next is close packing in a three-dimensional. Close packing in three dimension. Here also there are two possibilities. Here also there are same as that of in a two-dimensional structure. In two-dimensional in close packing two-dimensional also there are two possibilities. One is square close packing, another is hexagonal close packing. In close packing three-dimensional also have two possibilities. One is three-dimensional close packing from two-dimensional square close packed layers. Once again, I'll repeat, three-dimensional close packing from two-dimensional square close packed layers. See here, this is a two-dimensional square close packed layer. If just call it as a type. this layer is called as A type layer. Similar layer, just place the similar layer over this layer, first layer, and spheres of the second layer as well as spheres of the first layer exactly aligned in horizontally as well as vertically. Similarly, place the third layer over the second layer, and the spheres of the third layer and spheres of the second layer are exactly aligned with the first layer, horizontally as well as vertically. And if we place the fourth layer over the third layer, and spheres of the fourth layer are exactly aligned with the second layer as well as third layer as well as first layer. Hence, this type of arrangement is called as AA type arrangement. This arrangement are three-dimensional close packing from two-dimensional square close packed layers. This results simple cubic lattice. This lattice is result from this close packing structure. Okay, simple cubic lattice is formed. Okay, this is one way of arranging the spheres in three-dimensional. Another way is there, that is, see here, three-dimensional close packing from two-dimensional hexagonal close packed layer. Three-dimensional close packing from two-dimensional hexagonal close packed layer. This is the second way, second possibility we can arrange the spheres. Just see here, placing same here also, just take a two-dimensional hexagonal close packed layer, and placing the second layer over the first layer. See here, this is the first layer. See here, I have placed second layer over the first layer. Those spheres covering this void means what? Void means the empty space present between the spheres is called as void. It is a very important definition for 1 mark. Void means it is the empty space present between the spheres, that is called as void. But here, first, before placing the second layer, just see here, this is a one triangle here is there, just see here. Here I have not placed second layer over the first layer, only two-dimensional hexagonal close packed layer is there here. In this layer, two types of voids are created here. Two types of voids are there. Just see here, this is a one type of void in first row, and in second row another type of void is there, and these void are called as triangular voids. Triangular shape is there, hence these are called as triangular voids. These triangular voids are of two types. There in first row, these triangular voids are pointing upward. Apex of this void are pointing upward. In second row, the apex of the triangular voids are pointing downward. Okay, so these are the voids. Once again I will repeat, voids means the empty space present between the spheres, that is called as void. These are called as triangular void because the shape is triangular like this, triangular like is there, hence it is called as triangular voids. Triangular voids are of two types. So one is in first row, the apex of the triangular void is pointing upward, and in second row, the apex of the triangular voids are pointing downward. Okay, now see here, again come to three-dimensional close packing from two-dimensional hexagonal close packed layer. Here I have taken two-dimensional hexagonal close packed layer first. Now placing the second layer over the first layer, in such a way that the spheres of the second layer are covers the triangular void, covers the triangular voids. The apex of those triangular voids are pointing downwards. Just see here, I have not covered these void. I have not covered from the second layer, but by putting the second layer, the spheres of the second layer are covering here, covering the the triangular void, the apex of the triangular voids are pointing downwards. See here, just I am placing the second layer over the first layer. Second layer over the first layer. See, I am placing the second layer over the first layer. Okay. When we place the second layer over the first layer in this manner, we will get two types of voids. Here in detail I have written here two types of voids. That is, first void is tetrahedral void, second void is octahedral void. Tetrahedral void means this is the void which is formed by four spheres. 3 spheres from the first layer, 1 sphere from the second layer. See here, 1, 2, 3. These 3 spheres from the first layer and 1 sphere from the second layer. Between those 4 spheres, empty space is formed as present. That empty space, this is called as tetrahedral void. And again, just see here, and here see here. 1 sphere, here second sphere, here third sphere. These are the spheres of the second layer, and here see here 1 sphere, second sphere, and this is third sphere. These 3 spheres of the first layer. This diagram I have written here. A small picture I have written here. See, this is between these 6 spheres, the void is created here center. That void is called as octahedral void. Octahedral void means the void formed by 6 spheres, the 3 spheres from the first layer, 3 spheres from the second layer, and this is called as octahedral void. Okay. Now one more important concept is there here. If let the number of close packed spheres be n, these spheres, if the number of close packed sphere is n, the number of octahedral voids generated be n. Number of octahedral voids generated n. Number of tetrahedral voids generated 2n. Just as I said you, if we place the second layer over the first layer, during in that time, or if we placing the second layer over the first layer, in that time 2 voids are created. One is tetrahedral void and octahedral void. Okay, the number of tetrahedral voids and number of octahedral voids is depend on the number of the close packed spheres. If the number of close packed sphere be n, the number of octahedral voids are generated is n only, and the number of tetrahedral voids generated be, that is 2n. For example, if the number of close packed spheres are 10, the number of octahedral voids are generated be 10. And the number of tetrahedral voids generated is equal to 2 into 10 means 20. Okay, this is the relation between the number of close packed spheres and the number of octahedral voids and number of tetrahedral voids. Next, now we have placed the second layer over the third layer. There we have we get tetrahedral void and octahedral void. Now placing the third layer over the second layer. Placing the third layer over the second layer. So placing the third layer over the second layer in such a way that here two possibilities are there. During placing the third layer over the second layer, first there are two possibilities. First possibility, we can cover the tetrahedral void, or else another possibility, we can cover the octahedral void. Okay, first we are going to cover the tetrahedral void. See here, placing third layer over the second layer in such a way that the spheres of the third layer covers the tetrahedral voids, and this arrangement results hexagonal close packed structure. Hexagonal close packed structure. See here, this is a first layer and this is a second layer. Now I am placing the third layer over the second layer in such a way that the spheres of the third layer are covers the tetrahedral voids. See here, and this results HCP, hexagonal close packed structure. This, if we call first layer is A type and second layer is called as B type and third layer is exactly aligned with the first one, hence it is also called as A type layer. Hence this type of arrangement is called as AB type arrangement. Here coordination number is 12 because each sphere is contact with 12 of its neighbors, hence the coordination number is 12. Packing efficiency is 74%, means the total space occupied by the spheres in this structure, means hexagonal close packed structure. In that hexagonal close packed structure, 74% of the space is filled. 74% of the space is filled, hence packing efficiency is 74%. And this sort of arrangement is found in metals like magnesium and zinc. Okay, next another possibility we can cover the octahedral void by placing the third layer over the second layer in such a way that the spheres of the third layer are covers the octahedral voids. This results cubic close packed structure or face centered cubic close packed structure or else face centered cubic structure. Okay, here if we call the first layer is A type layer and second one is a B type because second layer is not aligned with the first one. Similarly, third layer is also not aligned with the second layer as well as first layer, whereas fourth layer is exactly aligned with the first one, hence this type of arrangement is called as ABC type arrangement. Here packing efficiency is 74%. Here also total space occupied by the spheres is 74%, hence packing efficiency is 74%. And here also coordination number is 12 because each sphere is contact with 12 of its neighbors, hence coordination number is 12 here also in CCP or FCC. And this sort of arrangement is found in metals like copper and silver. Okay,